All right, here we go. This is our first lecture video for distance learning. Let's see how it goes. So we're in the middle of this chapter talking about the radiation from the sun. And last time we actually met face to face, we left off at this slide here talking a little bit about how we can measure the concentration of ozone in the atmosphere. But what I'm actually going to do here is we're going to walk back a few slides in your lecture notes back to this picture here, just to give you sort of the context of what we're looking at here. So if you remember, when we were talking about ultraviolet light, there's three different regions of ultraviolet light, A, B, and C. UVA has the longest wavelength, but it has also the lowest relative energy. And then as we go from A to B to C, we go to shorter wavelengths and higher energy. And so what this ultimately means is when we talk about the impact this light has on different molecules, when we think about photons, basically the smallest particle of light you can have, when we think about photons with wavelengths of less than 242 nanometers in the UVC region, these are enough to actually break apart some of the bonds that are holding together oxygen molecules, O2 molecules. And so we need to have a high enough energy, in other words, wavelengths lower than 242 to break these. Anything that's less energy, or in other words, anything that has a longer wavelength than 242, say something like 250 or 260 nanometers, it's not quite enough to break apart these bonds. But wavelengths that are 250 or 260 can still break apart O3 bonds, this ozone bonds that hold together the ozone molecule. So anything less than a wavelength of 320 nanometers in the UVB region can break apart ozone bonds. So it doesn't have to be just in UVB. Anything that has a lower wavelength than this can break apart ozone molecules. Anything in the UVC, or even if you go further to smaller wavelengths, that can break apart ozone. But it has to have at least the amount of energy that 320 nanometer light has to break apart that ozone. And if you recall, the last time we met, we talked a little bit about the ozone layer, just basically a portion of the atmosphere here where we see a fairly high concentration of ozone compared to other regions. Yes, we see an increase in the ozone down here in the troposphere, but when you get to the stratosphere, there's a higher concentration of ozone. Doesn't mean that there's a lot of number-wise ozone molecules. In other words, there's not like there's a whole bunch of this. It just means that relative to the other molecules that are in the stratosphere, ozone is a fairly high concentration. Okay, so that gets us back to thinking about that piece of context. So what I want to think about here is why does light of a certain energy break ozone molecules, but not break oxygen molecules. And in order to understand that, we have to think about something called Lewis structures, which is the next topic here. So in order to do Lewis structures, we have to understand sort of the arrangement of electrons around these atoms that we've been talking about. We've talked about how many electrons were in an atom total, but within an atom, they actually could be in different locations. And so we usually call these things electron shells, where it's almost like you can think about like an onion. Think about Shrek here, but an onion has different layers, but any electrons in an atom kind of fill into different layers as well. And so when we fill in those electrons around those atoms, we fill in the first shell before we get a little bit bigger and go to the second shell. We fill that up, and then when that fills up, we go to the next shell, and so on. When we look at these shells, the shells kind of fit in nicely with the structure of the periodic table, where we see the first row, we can have a max of 2 electrons that fit in that first shell. The second row, we can get a max of 10 electrons and kind of continue on from there. So I want to look at just a smaller version of the periodic table. It kind of gets rid of a lot of the extra atoms that we want to look at right now. Here we're looking at the first 18 elements, so we kind of are missing all those elements that fit in the transition metal region here. But if you look here, we've got numbers above and numbers below each of these elemental symbols. The numbers above are basically the atomic number, right? Remember, this tells us how many protons there are in the nucleus of the atom. It also tells us how many electrons total there are in a neutral atom. Okay, so carbon is element number 6. It has 6 protons. That's the definition of a carbon atom, is it has 6 protons. If it's neutral, it also has 6 electrons. Okay. So that's the numbers in blue. The numbers in red refer to what is in the, how many a number of electrons are in the outermost shell. So for hydrogen and helium, those numbers are the same. The blue and the red are the same. They only have 1 electron or 2 electrons, and it's just one shell. So the number you get at the top is the same as the number at the bottom. When you go to the next row there, for lithium and so on, these guys, you're filling in electrons in the second shell. And so the top number is the total number of electrons still, but bottom number, though, is only the electrons in the outermost shell. Okay, so you notice that lithium here has 3 electrons total. 2 of those electrons are in the inner shell, just like filling in hydrogen and helium. And so when we come to see, okay, how many electrons are in the outermost shell, it's 3 minus the 2 that we had in the inner shell. So here we've got 1 electron in the outermost shell for lithium. And beryllium is going to have 2 because it's the next atom over. And so on. And that's great for looking at a table like this, but I want to look briefly here at a periodic table. Just a regular periodic table. So here's a regular periodic table. This is the from ptable.com. It's a great website, but it has a lot of extra information you don't necessarily need to know. But I just want to pull up just the basic outline of the periodic table that you see here, with all the extra atoms that we don't have on that previous table there. All you need to do is look at which column that we're fitting in. If we're in the first column, you notice there are hydrogen, lithium, sodium, and so on. All of these have 1 electron in their outermost shell. In fact, this particular periodic table is kind of fancy. You'll notice that here's potassium on the blow up of potassium here, right? That's right up in here, right? So potassium, you see 2, 8, 8, 1. Those are the total number of electrons in those 4 shells that potassium has there. So the outermost shell there is 1 electron. You'll notice that when we go to sodium, the outermost shell has 1, lithium, outermost shell has 1, and hydrogen, outermost shell has 1. So you can kind of do that across the periodic table. But what I want to focus on here is if you don't have a nice table like this, like if you're going to an exam or quiz or something like that, all you need to do is look at which column we're in. That tells you how many electrons are in the outermost shell. The thing you have to be careful of is we ignore these atoms in here, the transition metals. So 1, 2 electrons in the outermost shell, and then we skip ahead to the column of boron. Here we have 3 electrons in the outermost shell. So even as we move down to gallium here, there's 3 in the largest one, indium 3 in the largest one, and so on. And then next column over, there's 4. Next column over is 5, 6, 7, and 8. Okay. So that gets us to thinking about the number of electrons in the outermost shell for these atoms. So here's our first activity that we could do using the periodic table as a guide. So find a periodic table, look online, whatever you need to do. Don't cheat and look and do a search for how many outer shell electrons are there in this particular atom. You can do this. It's not too hard. So we want to figure out what's the number of outer electrons. We call these sometimes valence electrons, and I'll use that word over and over again. Figure out how many valence electrons are in an atom of sulfur, an atom of silicon, an atom of nitrogen, and an atom of krypton. Remember, we're going to write this onto a piece of paper, or you can do it in a Google Doc, whatever, or Word document, whatever you need to do. Save it, and then take a picture of that piece of paper, or take your document and upload it to the activity on Schoology. Okay. So go ahead and pause the video now and work this out. It shouldn't take you that long to do. Okay, so you should have been able to do that after you've paused the video. Hopefully you didn't cheat now, right? So when we think about sulfur, sulfur is in this column, sorry, this column right here. It's right below oxygen. It's in the 1, 2, 3, 4, 5, 6th column of just what we call the main group elements, not including those transition metals here. So since it's in the 6th column, that will mean it has 6 valence electrons. Let me go back here. I'll get this sooner or later. So we got 6 valence electrons for sulfur. You can do the same thing for silicon. You'll find out that it's right below carbon. It has 4 valence electrons. Nitrogen is in the 5th column, so it has 5 valence electrons. And then krypton is one of those noble gases. It's all the way to the right-hand side, so it's going to have 8 valence electrons. Okay. All right, so hang in there with me. We're going to go do some more things thinking about Lewis structures. So when we think about how these atoms behave, they have chemical properties that basically are dependent on these number of valence electrons. Okay. Now these elements, these atoms of these elements, they will react with other things in order to completely fill a given shell of electrons. So in other words, sulfur doesn't like to have 6. It's going to want to try and fill this so it has a total of 8 electrons in its outermost shell. So it'll be a lot like, let me bring this up here, a lot like argon or one of these noble gases. And you see here, sulfur that normally has 6 right now, if it somehow gains hold of 2 more electrons, it'll be like these noble gases. These guys are very, very stable for a reason. It's because they have their outermost shell of electrons completely filled. And everything else is trying to be like these noble gases, trying to be like Mike, if you're familiar with that commercial from the 80s. All right, so these atoms try to do that. Okay, now they can do this one of a couple of different ways. Okay, and we call this filling the shell of electrons meeting the octet rule, because we usually are thinking about 8 electrons. Okay, so they can meet this octet rule by doing one of 2 things. One is they can share electrons with another atom. Okay. So they can, get together with another atom and kind of share those between the 2. And this is what happens in a molecular compound. Molecular compounds, electrons are being shared between adjacent atoms. One thing I should note here is that the octet rule, there is an exception to the octet rule. There's actually a number of exceptions to the octet rule, but the most important one for us in this class is that hydrogen atoms only need to have 2 electrons to meet their to be happy, to have a completely filled shell. And if you look at the periodic table, it sort of makes sense. It wants to be like this helium over here. It just needs to have 2 electrons in its outermost shell to fill it. So covalent bonds, sharing of electrons between atoms, that's one way of meeting the octet rule. Another way is to transfer electrons from one atom to another. This is what happens in ionic compounds. Say, for example, here we've got sodium and chloride, sodium and chlorine. Sodium, going back to the periodic table, has 1 valence electron in its outermost shell. It just needs to give away 1, so then it will be like neon over here. You see if we can get rid of that 1 electron in the outermost shell, and it then would drop down to, okay, now we got 8. It fills it up. Chlorine, on the other hand, it just needs 1 more. It has 7 in its outermost shell of electrons. It needs to pick up 1 more to be just like argon. And so this actually works out fairly nicely for sodium and chlorine. They're almost perfectly matched. Sodium has 1 too many. Chlorine has 1 too few. If sodium matches up with the chlorine, it can give away its electron in its outermost shell to chlorine, and they'll both be happy. And that's what happens in these ionic bonds, is we see electrons that are transferred from one atom to the other. Okay. All right, so we use Lewis structures to represent these molecules or ionic compounds to show how we share electrons or transfer electrons. Usually we're talking about molecular compounds, so we use Lewis structures to show how electrons are being shared in a molecule. Okay. So we got a number of rules that we go through to draw Lewis structures, and you may have had chemistry before where you learned how to draw Lewis structures. I want you to be very, very careful because many of you may have learned this the wrong way or learned shortcuts that really do not help you out. So you need to unlearn what you have learned and relearn it so that you can get, just follow these steps systematically. And so if you do these steps all the time, you'll come to the right answer. Okay, so here's the individual steps for drawing the Lewis structure. So the very first thing you want to do is to count the number of valence electrons. Remember, the outer valence electrons are the outermost electrons. So count the number of valence electrons contributed by each atom in the molecule. So that's your first step. I'll walk through an example here in a minute. Step number 2 is you're going to basically add those valence electrons up. So you're going to add them up. So this is something you learned right in elementary school. You can do addition. That shouldn't be too hard of a thing for you guys. The third thing that we're going to do is that we're going to arrange the atoms. We're going to draw, we're going to write out the elemental symbols for each of these atoms, and we're going to place the atoms that are closest to the left bottom of the periodic table, and we're going to put those in the middle of the molecule. Everything else is going to be on the outside. Remember that hydrogen is always going to be on the outside. If you think about this, this should make sense because hydrogen can only ever have 2 electrons around it, which means it can only share a pair of electrons, and so it can never be in the middle of a molecule. It's always going to be on the outside. But when we draw these atoms that are part of a molecule, the ones that are the closest to the left bottom periodic table are going to be in the middle of the molecule. So if I come back to the periodic table here, things like francium are going to be towards the middle. Things that are up here at the top right, those are going to be more on the outside. Okay, and again, hydrogen is always going to be outside because it can't be in the middle. It can only form one bonding pair of electrons, one shared pair of electrons. Okay, so that's step 3, arranging the atoms. Sometimes they call this drawing the skeletal structure. Step 4, you place electrons in pairs, and you're going to draw them as dots. And you're going to draw those dots around the atoms, and we're going to add those dots until we meet the octet rule for each of those atoms. And we're going to start with the outside atoms first. And when we do that, remember, keep in mind that hydrogen only needs to have 2 electrons. So you're not really going to draw dots that aren't being shared. And again, I'll show you an example here in a minute. And then after step 4, if we need it, only if we need it, we're going to form what we call double bonds. Okay, this is where we start to share more than one pair of electrons between atoms. We only form double bonds or multiple bonds after we've met, if we need to meet the octet rule, only after all the electrons have been assigned. Okay, so if we've run out of electrons, we need to meet the octet rule. Okay, this is where we might start to form multiple bonds. And again, I've got some examples here we're going to work through. Okay, so here's our examples. We got 4 examples we're going to walk through. Okay. So first we've got water, H2O. So if you look at the periodic table, you'll find, of course, that hydrogen has 1 electron, and we have 2 of them, 2 hydrogen atoms, so I'm going to multiply that by 2. And then we also have an oxygen atom that has 6 electrons with it. Okay. So, and we only have 1 of those oxygen atoms. So if we take those and we add it up, right, we do okay, so there is a multiplication here, but if we add that up, that's basically 8 electrons that we have total to work with water. Okay. So we're trying to basically take all the electrons, total them up for the molecule. They all go into one pool or one bin, and now we're going to arrange our atoms, and then we're going to distribute all those electrons out of the bin. So first thing we're going to do is figure out which atom is going to be in the middle. Well, we said that hydrogen is never in the middle. That means oxygen needs to be in the middle. And then we're going to take a hydrogen and put it on the outside. So I'm going to put 1 hydrogen here. It doesn't really matter where you put the other hydrogen, or put either hydrogen. I'm just going to put them there. Okay. So that's gets us through step 2. So the next step is we're basically going to assign electrons as pairs or pairs of dots around atoms, and we're going to share electrons first to form a molecule. So I have 8 electrons to play with. I know that I'm going to have a pair of electrons here and a pair of electrons here between the oxygen and hydrogen atoms there. Okay. Now I could draw them like this, but a shortcut way of drawing this, rather than drawing dots for a shared pair of electrons, is sometimes what we'll do is we'll draw it as a line connecting these atoms. So we'll draw a line connecting the oxygen to the hydrogen on the right, and a line between the oxygen and the hydrogen on the bottom. Okay. Now remember, each of these lines corresponds to two electrons that are being shared between these atoms. Okay, so I've got 2 electrons here, and I've got another 2 electrons here. So a total of 4 electrons that are already drawn. Our next step is to draw electrons around the atoms so that we meet the octet rule. Now remember, hydrogen only needs 2, and so we're okay already. We count this pair of electrons here as accounting towards the hydrogen. We do a little bit of funny accounting here. Those of you who are maybe business majors, stuff like this, don't do this when you go out in the real world. We actually double count these electrons that are shared to count both for the hydrogen as well as the oxygen here. So we got 2 electrons around the hydrogen. That meets the octet rule for hydrogen. It's totally happy. Remember, it just needs to pick up an extra electron, so it has 2 electrons to be just like helium. So this hydrogen is happy, this hydrogen is happy here. We have, but this is 4 electrons. We started with 8. We have 4 more electrons left. And so we're going to draw those 4 electrons around the only atom that can pick them up, which is hydrogen here. So there's 2 there, and there's another 2. So if I sit there and count these all up, I'm going to need, remember, I need 8 electrons total. I've got 2, 4, 6, 8 electrons total drawn in the molecule. You get really good at counting by 2 when you draw Lewis structures. So we got 8 electrons around the entire molecule, all the atoms in the molecule. That's one thing that you're going to do to double check your Lewis structure. First thing to do is count up, do you have the same number of electrons that you went in with? We went in with 8, we have 8 drawn. The second thing you're going to do is make sure that you meet the octet rule for everything. So hydrogen only needs 2, we've got 2 electrons around this hydrogen, we have 2 electrons around the hydrogen down below. We take a look at the number of electrons around oxygen. I've got 2, 4, 6, 8. I've got a total of 8 electrons around oxygen. That meets the octet rule, so we're good. Okay, so this is the Lewis structure that we've drawn for water. Now, again, it doesn't matter where I've drawn the hydrogens relative to each other as long as one hydrogen is connected to the oxygen and the other hydrogen is connected to the oxygen. So I've drawn it this way so that one's to the right, one's to the left. I could have drawn this in this way, and it's perfectly okay. It's still okay. It doesn't matter which way I draw that. Okay. All right. Now for chlorine, the chlorine molecule we have on the right. So chlorine is group 7. That means it has 7 electrons each. There's 2 of those. So that means we have 14 electrons to work with. Okay, so I'm going to draw our backbone structure here. Here's chlorine. Here's chlorine. It's going to have 2 electrons that are sharing between it. I'm just going to redraw that as a line. Get into the habit of drawing this as a line. So there's 2 electrons that are already drawn. All right, so the next step here is I need to draw those other electrons there so that we meet the octet rule for each chlorine atom. So there's 2 around this, this chlorine atom. I'm going to draw pairs. So there's another pair there. That's now a total of 2 from the bond and 2 more from what we call lone pairs that are sitting on that chlorine atom there. That's 2, 4. There's 6 electrons total, and there's 8 electrons total. So at this point, I've drawn a complete octet around the chlorine here. So this chlorine is now happy. I have 14 electrons to draw from, and I've got, like I said, 2, 4, 6, 8 drawn right now. I have 6 more I can play with. I'm going to put those other 6 here on the right. Remember, I came to the math because I knew I've got 14 to start with. I've drawn 8 already, so 14 minus 8 gives me 6. 6 more electrons to draw around the chlorine. Here's 2, 4, and 6. Okay, so I should have total 14 electrons drawn. There's 2, 4, 6, 8, 10, 12, 14. So we're good on that. Then we need to meet the octet rule for everything. So I've got 2, 4, 6, 8 electrons around the chlorine on the left, 2, 4, 6, 8 electrons around the chlorine on the right. So we meet the octet rule for both of those. Okay, so this is a good Lewis structure for chlorine molecule. So look at the oxygen down in the lower left here. Oxygen is part of group 6. So that means there's 6 valence electrons in each oxygen atom. That's a total of 12 valence electrons we have to play with. So I'm going to draw the backbone here. There's 2 oxygen atoms, and then there's at least a pair of electrons that are being shared between them to hold them together as an oxygen molecule. So I have 12 electrons to play with. I've got 2 drawn already. Let's draw those extra electrons to meet the octet around the oxygen atoms. So there's another 2, there's another 2, and there's another 2. So that gives me 2, 4, 6, 8 electrons around the oxygen atom on the left. So that meets the octet rule. That's happy there. I've got 8 drawn so far. I've got 12 total to play with. So 12 minus 8 gives me 4. I have 4 left that I can draw. So I'm going to draw those remaining 4 on the oxygen atom on the right. So we've got now all 12 electrons drawn. 2, 4, 6, 8, 10, 12. Okay. And let's check the octet rule. We got 2, 4, 6, 8 electrons around the one on the left. So that meets the octet rule. 2, 4, 6 electrons around the one on the right. So I don't meet the octet rule for that one. There's only there's only 6 electrons and I need 8. So here's where we start to think about multiple bonds. I've used up all the electrons I can draw, and it means I need to have 8 electrons on one on the right. The way I could do this, I could do one of 2 things. I could take one of these electrons and share it as another bond here, or I could take one of the electrons on the left and share it as another bond here. I'm going to start with the one on the right, okay, just to show you that this may not be the way to go. So if I take away 2 of these electrons here on the right, and I put them as another shared pair, drawing another line there on the between the oxygen atoms, I see I still have 12 electrons, right? 2, 4, 6, 8, 10, 12. So I've still got the same number total. But I have 2, 4, 6, 8, 10 now that are around this oxygen atom on the left. So 10 exceeds the octet rule. I don't want to have 10. I want to have 8. The one on the right is 2, 4, 6. I still only have 6 on the right. So that's not going to work out. So I'm going to go back to what I had before. So I'm going to get rid of this second pair there. I'm going to put it back around the oxygen atom on the right. And I'm going to take now one of the electron pairs from the oxygen atom on the left. So let's remove those pair. Okay, and I'm going to make that as a second bond here. So double checked again. I got 12 electrons total. 2, 4, 6, 8, 10, 12. 12 total, so that's good. Now let's check the octet rule. 2, 4, 6, 8 around the left. That's good. 2, 4, 6, 8. 8 electrons around the oxygen atom on the right, so that's good. So remember, each of these lines here between the atoms, that counts as a pair of electrons. It counts as 2 electrons. So this is our Lewis structure for an oxygen molecule. Okay, so let's step it up a little bit here. Here we've got this molecule here. This molecule here has 2 carbon atoms and 2 hydrogen atoms. This is probably a little bit more complicated than I would give you in an exam, but I just want to show you the Lewis structures work for these molecules as well. So remember that we need to have hydrogen on the outside. It can't be in the middle. So I'm going to draw 2 carbon atoms, and they're going to be connected somehow, right? So this is supposed to be a line, a single line. Let me draw that again. So single line there. I'm going to draw a carbon atom on the, a hydrogen atom on the left. I'm going to draw a hydrogen atom on the right as well. Get rid of my scribbles on the screen. Okay, so this is a good place to start from, and in your case, you're not going to know exactly to start with hydrogens, one each on the carbon atoms, but I just want to show you the process here to get to the right answer. So to count here, I forgot to do my counting first. But we have 2 carbon atoms. Each carbon atom has 4 electrons around it. I also have 2 hydrogen atoms. Each hydrogen atom has 1 electron around that. So 2 times 4 is 8, plus another 2 gives me 10. So I have 10 electrons total around this molecule. By drawing my my backbone here, I have 2, 4, 6 electrons drawn. 10 minus 6 gives me 4. I have 4 left that I can draw. Now I know I don't want to draw them around hydrogens because they're perfectly happy as they are now. They only need 2. They have 2. So the extra 4 electrons I need can be put on the carbon atoms. So I'm going to do that. I'm going to put them on the one on the left here. So there's one pair, there's another pair. So I got now a total of 10 electrons. 2, 4, 6, 8, 10. Now let's check my octet. Octet is met for the hydrogen and that hydrogen there. 2, 4, 6, 8. 8 electrons on the carbon on the left, but I only have 2, 4, 4 on the right. So what I'm going to do here is I'm going to take these 2 electrons and remove them and put them as a double bond here between those 2 carbon atoms. So I should still have 10 electrons. 2, 4, 6, 8, 10 electrons total. 2, 4, 6, 8. I still have 8 around the carbon atom on the left, so that's still good. 2, 4, 6. I went from 4 up to 6, but it's not quite enough to meet the octet for the carbon atom on the right. So I'm going to do it again. I'm going to take another one of these electrons here and put it as we call a triple bond here between the carbon atoms. So I removed that electron pair from the carbon atom on the left. I put it here as another bond that's being shared. So let's count. We need to have 10 electrons total again. 2, 4, 6, 8, 10. So 10 total electrons, and then we need to meet the octet rule. So hydrogens are still good. They only need 2, and they have 2. Carbon on the left, I've got 2, 4, 6, 8. So we've met the octet for the carbon on the left. 2, 4, 6, 8. I've met the octet for the carbon on the right. Remember, a line is 2 electrons, and then we're double counting them. If we got a line drawn to it, to that atom, it's going to count both towards that atom as well as towards the atom it's sharing those electrons with. So this 2 electrons counts both towards this carbon as well as to the hydrogen on the left. All right, so that's our final Lewis structure for this molecule here. You notice it's got a triple bond there, and we only drew the triple bond when we ran out of electrons to draw, and we still needed to meet the octet rule. Okay. So, time to work through another activity. You don't need to do this on a sheet, although it may be useful if you want to upload it. That's fine. I could try and take a look at those. So here's another activity for us to work through. Draw the Lewis structure for each of these compounds. Don't forget, as you're drawing them, remember the rule. One of the rules is to figure out which atom is going to be in the middle. So the atom that's further to the left and down on the periodic table is going to go in the middle. So remember that when you get to that fourth Lewis structure there. So take some time right now. Go ahead and pause the video. Work on these. And I'll give you a few seconds to pause that. And then when you come back to the video, I'll show you sort of the answers to these Lewis structures. Okay, hopefully you gave it a good faith attempt. We're going to start with HBr here. Hydrogen has 1 electron that brings with it. Bromine brings 7. It's a group 7 element. And so that's a total of 8 electrons I'm going to draw. We're going to draw the hydrogen and bromine elemental symbols. We need to connect these somehow, right? So there's our pair of electrons that are being shared between them. So we've started already with 2 electrons around hydrogen, or 2 electrons being shared between hydrogen and bromine. I've got 8 total I need to draw, so 8 minus 2 gives me 6 left. Hydrogen is fine. Let's draw the remaining 6 around bromine. So we're going to draw again those as pairs. There's a pair, there's a pair, there's a pair. So it's 2, 4, 6. I've got a total of 8 electrons around the bromine on the right. I've got 2 around the hydrogen on the left. That meets the octet for both of those elements. Remember, hydrogen only needs 2. I've drawn a total electrons of 8. So that meets my 2 criteria for double checking. Make sure I meet the total number of electrons. I've got 8 total drawn, and I meet the octet for both atoms. Moving on for H2S. Okay. Now we know that hydrogen has to be on the outside because it cannot form more than one bonding pair between atoms. So I'm going to draw hydrogen there. I'm going to have sulfur in the middle, and I'm going to have another hydrogen on the other side. And again, I don't have to draw this in a line. I could draw them at an angle or whatever. It doesn't really matter. I've got 2 hydrogens and a sulfur. Each hydrogen is going to bring with it 1 electron. So 1 electron times 2 gives us 2. And I'm going to add to that the number of electrons around sulfur. We said that's a group 6 element. It's right below oxygen. It's going to bring 6 electrons with it. So that gives me a total of 8 electrons. Drawing the skeletal structure, I have to have bonds between the hydrogen and sulfur on either side. So I've drawn a total of 4 electrons already. 8 minus the 4 I've drawn gives me 4 to work with. 8 minus 4 gives me 4. Those extra 4 electrons are going to go around sulfur, just like that. Okay, so double check. I need 8 total electrons. I've got 2, 4, 6, 8 drawn within the whole molecule. That's good. Meet the octet. I've got 2 around the hydrogen on the left. I've got 2 around the hydrogen on the right. That meets the octet for hydrogen. I've got a total of 2, 4, 6, 8 electrons around the sulfur atom in the middle. That meets the octet for the sulfur. All right, let's move on to CO, carbon monoxide. Carbon brings with it 4 electrons, right? That's a group 4 element. And we're going to pair that with oxygen, which is a group 6 element. So we have a total of 10 electrons around the molecule of carbon monoxide. Draw the structure here, the backbone, carbon and oxygen. They're going to be linked together like this. I've already drawn 2 electrons here. So 10 minus 2 gives me 8 electrons to play with. I'm going to draw those extra 8 around the carbon atom on the left. Doesn't matter really too much where I draw this at. So if I look at this here, I've got a total of 2, 4, 6, 8 electrons around carbon. I can't draw any more around carbon here. I have 2 more electrons to play with. So I'm going to draw those extra 2 electrons around oxygen on the right. Okay. So remember, we're at the stage of assigning electrons. We assign electrons around an atom until we meet the octet, and then we move on to the next one. So I met the octet for the carbon on the left, and I had 2 electrons left, so I put them on the oxygen atom on the right. So I'm going to double check this now. I have 10 electrons total I need to draw. I've got 2, 4, 6, 8, 10 electrons total drawn, so that's good. And I need to meet the octet rule for everything. 2, 4, 6, 8 around carbon, that's good. 2, 4. I only have 4 around oxygen, that's not good. So I need to now take and share extra electrons between these. If I take and share this one on the right with the oxygen to share between the two atoms, that's not really going to improve my numbers around the oxygen atom on the right. So I'm going to, and it's actually going to make it so that I exceed the octet rule for the carbon atom on the left. So what I'm going to do is I'm actually going to start with these guys over here. I'm going to take the carbon atoms lone pair that I drew up top. I'm going to take those away. I'm going to make them as another bonding pair between the atoms. And I still have 10 electrons, 2, 4, 6, 8, 10 drawn total, so that's good. And I still have an octet around carbon, 2, 4, 6, 8, so that's okay. But I have 2, 4, 6, only 6 around hydrogen. I started with 4, so it's a step in the right direction. Now I'm going to take away a second pair from the carbon atom, and I'm going to put it as another bonding pair between the two. All right, so I still have 10 electrons drawn, 2, 4, 6, 8, 10. And now I meet the octet rule for everything. 2, 4, 6, 8. 2, 4, 6, 8 around oxygen. So that's my final Lewis structure for a carbon monoxide. Now for the last one here, sulfur dioxide, this is going to be a tricky one. Okay, so I'm going to draw this out. If I look at the periodic table, sulfur and oxygen, sulfur is below oxygen. We said that things that are towards the bottom left are going to be in the middle. Things that are at the top right are going to be on the outside. So sulfur is below oxygen. Sulfur is going to be in the middle of this molecule. Okay, so I'm going to draw sulfur in the middle. I'm going to have oxygen on the outsides. I'm going to connect those. All right, so I need to go back and count my electrons. I have 6 around the sulfur because it is a group 6, right? 1, 2, 3, 4, 5, 6, group 6. Oxygen is also group 6. So when I think about this here, I'm going to add this. I've got 2 oxygens at 6 electrons each. Add those all up. That's a total of 18 electrons. Sorry, I keep scribbling all over the screen here. So I've got 18 electrons to play with. I've drawn 4 already. I have 14 left I can put onto the molecule here. So I'm going to put those again. I think the best thing for us to do is to start with assigning electrons to the outside atoms. So I said I've got 14 to play with. I've drawn 2 already. There's 4 and there's 6. I'm going to stop there for this oxygen because I met the octet rule for it. So again, I've got 2, 4, 6, 8, 10 drawn so far. I have 18 to play with. I have 8 more to draw. I'm going to draw some more around the oxygen on the right. So there's 2, 4, 6. Okay, so I've completed the octet on the right. Again, just double check here. I got 2, 4, 6, 8, 10, 12, 14, 16 drawn total. I have 18 to play with. 2 more electrons, right? I've drawn 16. I can do 18. I have 2 more left. I'm going to put those now on the center atom there, the sulfur atom. So there's the last 2. So double check here. 18 electrons drawn total. 2, 4, 6, 8, 10, 12, 14, 16, 18. Then I check the octet. 2, 4, 6, 8 for oxygen on the left. That's good. 2, 4, 6, 8 for oxygen on the right. That's good. 2, 4, 6. Only 6 for the sulfur atom. Okay, and I need 8 to meet the octet rule. So I'm going to take a pair from one of these oxygen atoms to share it to make 8 for the octet for sulfur. Okay. So again, I'm going to take it from the outside here. If I take it from the middle here, I'm not going to change the number around the sulfur, and that's not going to help me out. So I'm going to take from the outside. I'm going to take this pair here from that oxygen atom and make it as another bond between the oxygen on the left and the sulfur atom. Okay. So I've drawn this. So I still have 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 total. I've got 2, 4, 6, 8 around oxygen. 2, 4, 6, 8 around this oxygen. 2, 4, 6, 8 around the sulfur. Okay, so that meets the octet rule for everything, and I've got 18 electrons drawn. This is a good Lewis structure for sulfur dioxide. Now, if I was to go back and do this again, let's say I draw it in the same relative positions. And instead of taking the electrons from the oxygen atom on the left, if I was to take those extra electrons from the oxygen atom on the right and form a double bond here, this is an okay structure to draw on too. If I get it actually so it's a dot and not a scribble there. Okay, so this, I could have drawn this Lewis structure and it would have been equally correct compared to this one up here. All right, so we're going to come back to this sort of thing where we could draw 2 equally correct Lewis structures in our next lecture video later on. right, so that ends it for this lecture video. Sorry, it's actually fairly long, but hopefully when I go forward here, I'll start to try and break these down a little bit smaller so we don't have as long of a video, but we still need to cover this amount of material in a given day. All right, so don't forget for these for the activity, if you wrote it down on paper, take a picture, upload it to Schoology under the activity. I believe this is, I'll check here real quick here which activity it is. You won't have it on your screen, but I believe this is activity number 11. So upload it as activity number 11, and then I'll talk with you the next time we have another video.